Hello, everyone. How are we doing today? All right. So this is our final section in chapter 3, and what we're going to be focused on today is what happens to our set of differential equations that we've been studying when we have the non-homogeneous case. All right. So we, of course, simplify our equation here to be focused on a linear equation with constant coefficients. To get this, and under these conditions, we have characteristic equation looks like so. The characteristic equation is going to have roots that look like negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And for the purposes of the discussion that we're going to be having here today, we are going to define lambda so that it's equal to a non-negative value of b over 2a. And if we do that, then this expression above becomes negative lambda plus or minus the square root of lambda squared minus c over a. We accomplish this by pulling the 2a inside the square root. The 2 becomes a 4 in that instance. We get an a squared in the denominator, and it all simplifies to this. And if we further define mu to be equal to that radical, with a sign change underneath the square root, then we end up with the roots of our characteristic equation being negative lambda plus or minus I times mu. Okay. This mu ends up with a special name. This is called the frequency response. Okay. We're setting all of this up because we want to be able to talk about what happens to systems where we have motion other than purely oscillatory motion. Okay. So in a situation where we are going to have complex values for the roots of the characteristic equation, we know that the homogeneous solution is going to have the form y of t equals e to the minus lambda t times c1 cosine mu t plus c2 sine mu t. All right. So when lambda is equal to 0, which means that our differential equation is undamped. Okay, that's when that happens. This gives us a situation where our frequency response is just equal to the natural frequency. Okay, remembering that C is equal to K, B is equal to gamma, and A is equal to M. Okay, so we tend to refer to this as omega naught. Okay, and a lot of the interesting dynamics of the system happen to do with looking at what's going on with this relationship here. Okay, when the value for lambda is positive, we're going to have a damped ODE. Okay, so for positive lambda, motion will be defined by a quasi-periodic transient solution. Okay, what that means is that this term here will be present in the equation because of the way that we have defined things. Lambda's positive, so this exponential is going to be decaying. Okay, and what that's going to do is it's going to take this solution and crush it. Okay, I'm multiplying it by a number that's reducing down to 0. Okay, so eventually this entire term will vanish, okay, or become very, very small. All right. The only way to prevent the differential equation from being reduced to 0 is to have some kind of external forcing function, which would be the purpose of the non-homogeneous part here. Okay. We have a function g of t that we apply on the right-hand side. This gives us a particular solution to the ODE. Okay. It generates what's called a forced response. We know that having a non-homogeneous equation will result in us having a particular solution to the differential equation. The particular solution is interpreted as the forced response of the system. Okay? the natural behavior of the system in the absence of external forces is going to be the one given to us by the homogeneous solution of the differential equation. It's just defined by the system parameters. For the oscillating mass, just the weight, the damping, and the spring constant. Okay. But if we apply some other force to this system, then we'll get a force response. It's just another term by which we refer to the particular solution. All right. Okay. So let us look at finding the steady state response. What we're going to have is this. I don't want to copy a bunch of stuff, so we're going to cheat. All right. So we have a spring that's readable, right? Okay. We have a spring that's stretched by stretched 6 inches by a mass of 8 pounds, and we have a dash pot mechanism like the one that I described at the end of last lecture that has a damping constant of k equals 1/4, and we have an external force given to us by 4 times cosine of 2t. All right, what we want to do is determine the steady state response. So we start off by writing down our equation. Wrote it a y instead of a u. Yeah. General form of the equation looks like this. You can plug in the values for it. Okay. I have a couple of things to figure out. We need to figure out our mass value. Okay. We're told that the mass is 8 pounds. We will use 32 feet per second squared as our approximation for mass. I'm sorry, the acceleration due to gravity. Pardon me. Oops. Okay. And 1/4 pounds squared per foot is the unit for slugs, which is the mass unit in the imperial system. Okay. We're given gamma as 1/4 pound seconds per feet, and we need to figure out k. I'm sorry. Wait, hold on. Okay, sorry, I made a mistake. This is the typo. This should say gamma there. have to fix that one. Sorry about that. Okay, putting all this together, we have a differential equation That is 1/4 u double prime plus 1/4 u prime plus 16u equals 4 cosine 2t. And taking this equation, we'll want to multiply by 4 in order to simplify things. Gives us this expression here. And so now it's just a matter of putting all of this together. We determine our characteristic equation. So r equals -1 plus or minus the square root of 1 squared minus 4 times 1 times 64 all over 2. This is going to give us -1/2 plus or minus 4 times 64 is 256. So we're going to have the square root of 255 over 2 times I as our value for the frequency response, right? Okay. And so our homogeneous solution is going to look like e to the negative t over 2 times the quantity c1 cosine square root of 255 over 2t plus c2 sine square root of 255 over 2t. Our right-hand side is not linearly dependent upon this. Okay, so we could get away with using the method of undetermined coefficients in this problem because that right-hand side is simple enough to permit it. So we will do that. We will guess that our particular solution is equal to a linear combination of sine and cosine. Take the necessary derivatives. Put all that together. Okay. I don't know why I switched to y in the middle of the problem. Okay, sorry, I got that fixed. It doesn't matter if you call it y or u or whatever. Just wanted to be consistent. All right. So now what we do is we take these, plug them back into this equation. So instead of doing a bunch of extra copying, we can see that let's work this out. For cosine 2t, Gonna have 64A here. People are out there trying to break stuff. Okay. We will also have 2b cosine 2t. Plugging in cosine to replace u prime. And then we will have negative 4a, right? Okay, this kind of shortcut is confusing. There's no reason not, you can just plug it in and do the computations otherwise. I'm just trying to save us a little bit of time here. All right. Similarly, 64 copies of B for sine, negative 2 copies of A, and negative 4 copies of B. Okay, so that is 60A plus 2B times cosine 2t plus negative 2A plus 60B sine 2t. That has to equal this, coefficient to coefficient. So this needs to equal 16, and this needs to equal 0. We can set up a matrix equation for this. $60 and negative 2 is where that comes from. 2 and 60 is where that comes from. Okay, and then the right-hand side is given by that. The determinant of this matrix is 3,604. 60 squared is 3,600 minus negative 4. We can use Cramer's rule in order to do this evaluation. We get 16 times 60, which is 960 minus a 0 over 3,604. This fraction simplifies a little bit. You can divide both by 4. For B, $60 times 0 minus negative 16 times 2 gives us 36 over 3,604. Again, they're both divisible by 4. And so our particular solution, that is the steady state response, sorry, 32. Thank you. All right. So writing out the steady state response here, we have this. This is our particular solution. The reason this is called the steady state response is because the transient solution will eventually be overtaken by the external forcing on the system. Okay, so it'll decay away, and then we'll be left with what's going on with the other solution of the differential equation. Does it make sense? Okay. All right. Now, there are several interesting phenomenon that can happen for this particular system. If we start with the same differential equation, okay, except we are going to allow m to now be a variable, okay? We could redo this problem while looking at a particular solution of this form, okay? Except we are on purpose not specifying the value of omega because we want to figure out what the optimal omega is. What I want to do is I want to figure out the omega that makes these values the biggest. If I take the overall amplitude, which would be the square root of the sum of their squares. Okay, so it gives me the biggest amplitude in my steady state response. Okay, if we set this up this way, I will show the notes page because there's a lot of algebra that goes on here. All right, but we just find the particular solution. Okay, we put everything in, and what we can do is we can, like we just did, solve the matrix equation to tell us what the values of A and B are, except those values of A and B are going to be dependent upon what the particular values of these coefficients are. Okay? We look at the amplitude R by taking the versions of these coefficients, putting them all together, and then this gives us a function for R squared that depends on M. M is the only one of these things that isn't that's not fixed. Okay, W depends on, or omega depends on what value it is we choose for the mass. So in order to maximize this, we use calculus. We take the derivative of this expression and we figure out that the maximal value for M is going to be 4 slugs. Okay. So if we plug in m equals 4 into our expression, what happens is we can take a look at this graph and we see that the amplitude of the steady state response has a huge spike if we choose this value, okay? And that is very, very large compared to the amplitude that we get from the steady state solution for these things, okay? Here, m was equal to 1/4. Okay, if we take the square root of the sum of the squares for these values, we're over here in this chart. Let me not see my cursor. There. Okay, so I have to click on it to show my cursor. Okay. We're at this point in the graph. If we choose a larger value for m, we will see the values of those coefficients get very, very big quickly, comparatively. All right. Now, this is important because if you are designing some kind of oscillator, you want to be able to understand how you choose these parameters in order to get certain kinds of behaviors. All right. If you want the most wildly oscillating system in that you can have relative to the parameters, you would there's an optimal choice for mass. Okay, picking more mass doesn't make it have larger amplitudes oscillations necessarily. All right, it is going to be dependent upon the external forcing and what the values for the damping and the spring constant are. Okay, these things go together. This is especially important for the other type of application that we didn't have as much time to talk about last lecture, which are electrical vibrations. Okay, we can, using the same kind of differential equation, also examine what goes on in RLC circuits. Okay, those of you who are here with us, how many of you have seen this before? Familiar with RLC circuits? Okay, and somewhere in the neighborhood of a third of you. All right. So this is a very common example for a second order differential equation. The way that we determine the equation here is we set up using some standard electric laws and come up with this second order differential equation in terms of the charge as a function of time. Yeah, that's what Q is in this instance. All right. L is the inductance, R is the resistance, and C is the capacitance. Okay. When you're setting this up, please remember that this C is in the denominator. Okay, it's really easy to mess that up. And then for these examples, some of the numbers look wild because they tend to be chosen for realistic, more or less, circuits. Okay, so you'll get some big orders of magnitude differences between these things, but it typically works out. Okay, and especially for exams and things, I'll pick numbers that make sense. Okay, but for these types of systems, those oscillations are very, very important because those oscillations correspond to signals that could be sent or received by these types of objects. All right. So if you have electronic antennas, this is how they work sometimes. All right, is by actually controlling the frequency of what's going on in the circuit itself. Okay, so having this level of control, being able to maximize the amplitude is very important because the thing that you're detecting is the field that is being generated by the oscillation of the electricity traversing the circuit. All right, maximizing that amplitude sends the strongest signal. Okay, or on the opposite end, sending a signal at the correct frequency excites the detector the most it can be excited because you're matching its natural frequency and interacting with it that way. So these ideas are connected. I know it seems, especially if you kind of scroll through the notes pages here, seems like a lot of stuff, all right? But That's because we're setting up these formulas. They're a little bit complicated if we do them purely symbolically, but that's the purpose that's driving the example here. Okay. So what we're doing here makes sense? All right. So let's talk about a couple of specific examples. There's another example like the one we just scrolled through that shows what happens, or that you can maximize also the steady state as a function of frequency. Algebra looks pretty similar, all right? But there is a very important example that I want to show. Where is this thing? All right, there we go. Okay. Well, let's work through this. So what we're going to have is this differential equation here, u double prime plus u equals 3 cosine omega t. We're going to set both of the initial values equal to 0. Okay. And we are also going to specify that omega, whatever it is not 1. Okay. So we're not going to specify this value here. Okay. What we're going to do is we're going to solve the initial value problem for these values of omega. We're not going to plug in the numbers and solve the problem 3 times. We're just going to leave omega there and then come up with a formula and then deal with it at the end. All right. Okay. So let us get started here. Characteristic equation for this differential equation is pretty easy. All right. It tells us that the homogeneous solution is C1 cosine plus C2 sine, just of t. The fact that these are just t's tells us why omega is not allowed to be equal to 1, because then the right-hand side would be linearly dependent upon our solution, which we don't want. Okay. All right. So now what we're going to do is we are going to look at a particular solution for the differential equation. We're going to guess that it looks like a cosine omega t plus b sine omega t, and do the work in order to set ourselves up to be able to plug this in. So we compute our derivatives using the chain rule. End up with 1 and then 2 factors of omega. And then we take these, which are the only ones we need because of the differential equation, plug them in. So what we're going to end up with is a 1 minus omega squared, factor out the a, cosine 2t, sorry, cosine omega t, plus b times 1 minus omega squared sine omega t equals 3 cosine omega t. Make sense? This is equal to 3. This is equal to 0. Gives us a very simple system to solve. Because since omega squared can't be, or since omega can't be 1, that can't be 0. Right? So that's what forces b to be equal to 0. Okay. So that is to say that our full solution is equal to c1 cosine t plus c2 sine t plus 3 over 1 minus omega squared cosine omega t. We now want to solve the initial value problem in order to determine the values for C1 and C2. We compute the derivative, negative C1 sine t plus C2 cosine t plus 3 omega 1 minus omega squared. This is negative, and then sine omega t. Will make sense? Okay. U of 0 is equal to 0. So C1 plus 3 over 1 minus omega squared. So C1 is equal to negative 3 over 1 minus omega squared. U prime of 0 is equal to C2. I plug in 0 for the other two things to get sine of 0 in both cases. So C2 is 0. Okay. So we now have our differential equation, which we can write as u of t is equal to 3 over 1 minus omega squared times the quantity cosine omega t minus cosine t, because I take the minus sign and just reorganize the terms, right? So we get negative value, negative, we get negative this for C1. Well, seems decent. But in order to show some important effects of what the solution looks like, we're going to work on this a little bit. Okay. These expressions look very close to one another. Okay. So what we're going to do is we are going to use some trigonometric identities. If I have a cosine of u plus v, this is cosine u times cosine v minus sine u sine v. And cosine u minus v looks like cosine u cosine v plus sine u sine v. All right. The reason that we do this way is because if I take these expressions and subtract them, so if I take this minus this, these go away, and I'm left with two copies of this. Okay. The reason why that's important is because it allows us to take a sum and turn it into a product. Okay. So if on this side here, we imagine that 2u is equal to wt plus t, and u is equal to 1 plus omega all over 2 times t. We can similarly have 2v equals this, where we're subtracting t, and then v is going to be equal to 1 minus omega all over 2 times t. This satisfies the requirements of this equation for these things. Okay, so it turns this into this expression. Okay, we care about doing that because now I can write u of t as 6, because we pick up a factor of 2, over 1 minus omega squared times sine 1 plus w all over 2 times t sine 1 plus omega over 2 all over t. Okay. So that's a lot of stuff going on here, right? And the reason why we want to do such a thing is that now we have a value that we can plot. So taking a look at this, we'll set u of t equal to 6 over 1 minus, we'll use w here instead of omega, sine, and then we have 1 plus W over 2 times T, and then sine 1 minus W over 2 times T, and then we'll add our slider. We'll have to go from 0 to 1, and okay, thank you. I made that typo too many times. All right. Okay, so we're going to have to zoom out a little bit in order to see what's going on. Okay, so if we set I don't want to look at red. I like orange, but that's too bright. Anyway, okay, so this is the first of these that we were instructed to plot. Okay, we see that we have some dynamics going on in the system. Okay, and we have kind of this wave that looks a little staticky, and we're not really sure what it means. Okay, but if we move up to our next value, 0.8, maybe it's a little bit more clear what it is we're supposed to be looking at. Okay. Now, the idea behind what's going on here is that this first, we see on screen two pretty clear waveforms. All right. Now, the waveforms are being constructed here because of the interactions between these two different functions. If I plot them individually, we see the different effects that they have on the system. Okay, scroll out a little bit. Look at one of them at a time. Okay. The first of our factors, the sine of 1 plus W over 2 times T, is what controls the low scale oscillations. All right. We can see how this function here, all right, maybe it doesn't need the full amplitude, so it's kind of we'll make it bigger so it's easier to see. Anyway, you can see how the oscillations within the bigger waveforms are being controlled by what that function's doing, right? Whereas the other one controls the larger scale oscillations. Okay. This object here, if I have multiple waves interacting, is known as a wave packet. Okay. And you can describe what's going on between these two things as being within the envelope of the wave. All right. Now, if I have multiple waves interacting with one another, which is what these things are doing, okay, it also creates what's known as a beat. And if we go up to 0.9, okay, we see a much larger interaction of waves. Okay, an outside observer is going to experience this apex here of this much higher frequency wave all activating together simultaneously. All right. When you're listening to music, this is what happens. You have multiple waves that are all constructively interfering, especially say in sequence with what's going on with the percussion in a song, to all make noises at the same time. All right, and this is why music sounds bad when the timing is off, because all of the waveforms are not interacting together to create this effect. Okay, and in the example of this particular function, there's a reason why we're not allowed to have our W go to 1. Okay? If the forcing function on the right-hand side has a frequency that is close to 1, which is the natural frequency of our oscillator, if we push it to that limit very carefully, we see that the waveform explodes as that frequency gets closer and closer to 1. Okay, look at those amplitudes. It keeps going, all right? Now, what is this called? Resonance, all right? Whenever you've seen a commercial of some opera singer or something hitting a high note, and you've got the wine glass that's vibrating to the point to where it shatters, this is the mathematical representation of that phenomenon. There is a forcing function being applied to that system at a close enough frequency to its natural frequency for it to undergo this phenomenon. It is being exposed to force vibrations that take it beyond the physical limits of its system capacity. All right? Whatever this is, it probably can't handle an amplitude of 700. Okay? Especially considering where we started out with our initial values. Okay? It wants things to be way down here. Okay? So when we talked earlier about setting up our assumptions for these things, about not breaking the system, okay, this is the kind of thing we want to avoid, right? Okay, so, and you can also do this with electric circuits too, okay? You can very easily break them by putting them in a situation to where they're being exposed to something at the natural frequency via a forcing function, okay? It doesn't shatter if it's electric, it melts, right? Because the charge of the circuit is going to exceed the physical capacity of the system to be able to handle it, and something's going to break. Okay, the best thing that it can do is melt. The worst thing that it can do is short and have a giant electric discharge in some random direction affecting some other system. Okay, but mathematically this is what's going on, and you can break it down into the effects of these two components, which is why we went to the extra trouble of doing the trigonometry there. All right. So the exercises in this section, all right, are focused on just asking you to do otherwise normal chapter 3 problems with the added overhead of some extra vocabulary. Okay. So what I think I've already posted the quiz, haven't I? Remember to do that? Okay. I remember to do it. I did it early this week. So take a look at that. There's a problem similar to this example that we just did. Okay. I want you to do the work of being able to express it in terms of the sine and cosine product. Okay. Use the sum and difference formulas for cosine in order to be able to set that up. It's very similar to this example. And Otherwise, it's just a matter of putting all these pieces together, right? The other thing, and there's a couple of examples of this in the online notes as well, is making sure that you correctly interpret the information in the word problems to figure out what the mass is or spring constants or whatever. All right. Use sensible approximations for gravity, 9.8 meters per second squared or 980 centimeters. Yeah, centimeters per second squared. Does anyone have any questions? Yes. Oh, okay. So if we go above 1, we end up with a less interesting solution because basically the system can't respond fast enough. The forced oscillation is so much higher frequency than the normal behavior of the system that it kind of gets stuck. And if we greatly exceed that value, then it basically goes to nothing. So the resonance phenomenon will happen if we do approach the natural frequency from above or below, though. Okay, so numbers slightly larger than 1 are really bad. Numbers slightly smaller than 1 are really bad. Okay, and that should be fairly obvious from the fact that we have 1 minus omega squared in the denominator. Things that make that close to 0 are bad. Which is why it's nice to have it written in this form. Okay. Other questions? I need to finish getting those together. That is, those scores will be in before I allow myself to go on break. Okay, I might need the weekend, but it's on my list. I meant to try to get them done this week, but I have too many things for other classes that had to get set up. I have an extra class that I teach not today, but on Tuesdays and Thursday evenings, and that one's hard to get ready for, and it takes my extra time, which is very unfortunate. But I will get caught up on that. Thank you for asking. I needed somebody to keep me accountable. Anyway, that's where we'll do it. So finish the quiz. If you have questions, send me an email, and I will do my best to work on those. And otherwise, we will come back. When we come back, we will be getting ready for a Chapter 3 test. Okay. It might be. Hold on. Let me double check the schedule. It'd be a Wednesday because we meet on Wednesdays. But yeah, we will be reviewing and then taking the exam. The choice was exam before break, which was bad, and then the other choice is the exam after break, which is also bad. But there's more time to prepare for that. Okay, so we'll review. Yeah, whatever the date is. I'm very close to having the syllabus in front of me. Yeah, yeah. So the 20 Wednesday the 22nd, we'll talk about chapter 3. The test the schedule says the chapter 3 and 4 exam, but chapter 4 is just chapter 3 with more stuff. Don't worry about it. We're not going to talk about it. Okay. We have to do this way because we need time to deal with chapter 5 and chapter 6. Okay. Chapter 3 is pretty easy. I think we all understand that by now. The only thing that's kind of confusing that will take a little bit of time to absorb is the vocabulary from the last couple of sections. All right. Your time to do that is now, and like in the couple of days prior to coming back from break. All right. Make sure that's set up. And then as you're going through this material, start collecting the information that is relevant to you for, say, like a note sheet for chapter 3, because that will be something that you'll be allowed to have as well. So just get that together. You're allowed to have reminders about the vocabulary, what the different constants mean, okay? And then we'll talk more specifically on Monday about exactly what you're allowed to write down, for instance, about how to remind yourself how to set up a method of undetermined coefficients and variation of parameters. All right? Take care, and I will see you all in a while.